Okay, so this is Math341, according to my calculations, lecture 8. And what we're going to be doing today is conditional probability. Okay. So almost all probabilities in the real world are conditional probabilities. You have a result that depends on various other things. And the idea is the more information you know, the more this should inform your determination of what the probability will be. Right now, the Red Sox are playing extremely well. I'm happy as a Red Sox fan. If I ask you what's the probability the Red Sox will win their next game, what would you guess? Really high, because the Sox are always playing. But what might you want to know? Yes? Who they're playing. So I was at a North Adams Steeplecat game in the summer, and the visiting team didn't leave on time and did not make it to the game. And so they had to delay the game over an hour. And it was unclear for a while if they were going to arrive. So I said, look, I coach a bunch of first and second graders. Give me half an hour, I'll field a team. We'll play. They decided, no, my kids could run around on the field and do various things like that, but they were not going to have the Steeplecats college summer league team play my kids. If that game happened, what would be the probability the Steeplecats would win? I would say 1, yes. I would not even give us an epsilon chance. Although we would have great strike zones, yes.
Actually, it'd probably be pretty low. They wouldn't because they might throw the game so that the little kids wouldn't be happy.
There is a danger of that. Years ago, the Red Sox had a father-son game, and one of the kids actually made contact, and he ran to third base because that's where his dad played. And so exactly. So they gave him a triple. So there is a little danger like that. But knowing what's going on will affect your probabilities. So the whole point of conditional probabilities is if I tell you something is going on, it narrows down your outcome space. And what you should really view it as, you're doing a whole new theory of probability, but on a restricted place, so you're updating your probabilities. So we use P of A given B, or sometimes, if I want to use more chalk, probability of A given B to be the probability of A given B. So this is how we're going to write our conditional probabilities. There's a formula for conditional probability. We will essentially prove it, but before we prove it, I want to try to guess what the formula is. This is similar to what we did earlier in the year for the probability of A intersects B. This is a straight enough example that we really don't need to do this overkill, but this is one of the things I want you to take out of this class. How do you look at something new and get a feeling for what the answer should be? We did this for the rule for what the derivative of a product should be. It's not the product of the derivatives. We looked at x to the n times x to the m. If you want, another good example would be sine of x times cosine of x. Because we know sine of x times cosine of x is 1/2 sine of 2x, and then we could actually figure out what the derivative of that is and piece things together if we actually remember our trig identities. Given how many people remember trig identities, that's why I chose to do things like x cubed times x to the 4th. Okay? Let's try to figure out. Here is my first thought. The conditional probability of A given B is some function of just the probability of A and the probability of B. So if you tell me the probability of A and the probability of B happening, I can figure out what the probability of A given B is. Okay, I see at least one person shaking their head, and they don't seem to have their head going down, so they're awake, so I'll take that as a no. So this is the simplest thing I could think of. And I'm giving myself complete freedom in what this function is. Maybe it's the exponential of the square root of the cosine of the arctangent. I'm allowing myself anything. Okay? How can I disprove all of those? And this is related to the question we had before the start of class on the Monty Hall problem, which I have not forgotten. How can I disprove this? Yes?
Well, consider a coin flip and then any other event where the probability of both A and B is like 0.5.
Okay, so what we're going to do is we're going to look at an extreme case. And what I'll do is in one case, I'll take maybe A equals B, and the probability will be 1/2. And in the other case, I'll take A equals B complement, and the probability of each is 1/2. So in both cases, I would get a function of 1/2, 1/2. So if A equals B, what's the probability that A happens given that B happens? Has to be 1. If A is B complement, what is the probability that B does not happen given that B happens? 0. So it's impossible. So there's no way to do it. This is the power of looking at extreme cases. What's the most natural thing to try? A equals B. A equals B complement. What's the most natural probabilities to try? I chose probability 1/2. I didn't need it for this problem, but what would be other good choices to choose for probabilities? 1 and 0. So this should be your go-to bag. Okay? And so this tells us it's not even worth trying to search the space. Okay. Has everyone written this down? All right. This is so wrong, this does not deserve to be left on the board. All right? This has to just be removed. Absolutely unreasonable. So we need to refine our stuff. It can't just depend on the probability of A and the probability of B. Can anybody think of another thing that it might depend on? Yes? Probability of the intersection. The joint probability. So the probability of A intersect B is the probability that both happen. So maybe there is some function like this that would work. Okay? Now the question is, what's the most general thing? Well, I want to look at the probability A happens given that B happens. The most natural thing to think about is I'm now restricting my space, and maybe before 80% of the time B happens. But now I'm adjusting all probabilities so that now 100% of the time B happens. So a very natural guess would be it should be something over the probability of B. And in one of the homework problems, I was looking at alpha times the probability of A plus beta times the probability of A intersect B, and trying to figure out what would be good choices of alpha and beta. This is a nice general combination of my events. Okay? There's, of course, more complicated formulas you could come up with, but this is the simplest one I could think of. We could also just go straight to the, and let's just try the probability of A intersect B divided by the probability of B. So if we look at what's going on, here is the entire outcome space. Here is B, and here is the set A, and here's A intersect B. And if you think about what's going on, what's the probability that A happens given that B happens? Is now I look at what was the original probability of this, what was the original probability of this, and I'm claiming take ratios. Another way of looking at this is the expected counts approach. Let's say B happens 211 times. I have no idea why I wrote that. Maybe I'm into Fibonacci's. All right? And let's say A happened 53 times, and of those 53 times, maybe 3 of them were in A intersect B. So what I'll do is maybe I'll draw the 53 pointing into A, and so I would have 50 times in here. And so now, what's the probability that A happens given that B happens? Well, if A happens and B happens, the only events that could work are these ones here in A intersect B. And now, how many times did B happen? 211. Of those 211, 3 of them had A happening. So I would say that the answer should be 3 out of 211. And that gives me the probability of A intersect B over the probability of B. So I really like the intuition that the expected counts gives. So I'll use the same example that's in the book. I think this is a fishing problem. So we go fishing, and we have the following rules. We stop once we catch a fish. So we will catch either 0 or 1 fish. We have a 40% chance we get a trout, a 25% chance we get a bass, and a 35% chance we get nothing. Okay, and we want to calculate, I think, what is the probability that we would catch a trout? Given that we catch a fish. So, given we get a fish, what is the probability it is a trout? Just looking at this, what kind of answer can you give me? Without doing any detailed calculations. What can you tell me about the answer? Yes?
You can add up, like, so think of it as out of 100.
Right.
Add up trout and bass.
But I want to say, structurally, what can you tell me about the answer? Do you know anything about the number? Yes?
It's more than a half.
It's more than a half. Right? Before we do any calculation, it's more likely that we catch a trout than a bass. So if I know that there's a fish, I would be shocked if I got that the probability that it's a trout is less than a half. So what you were giving me was how to actually solve the problem. But before I even do the solution, I want to get a rough sense of what do I expect the answer to be. And I expect the answer to be at least 50%. So one thing in problems like this is to assume we have a nice number and look at all the different cases and see how it flows. So everything here is multiples of 5. So if I deal with multiples of 10, I'm going to be safe. I will start off with 1,000 days. Okay? This is probably more than I need. Probably 100 would be sufficient. I like to just pad it to have extra freedom in case I've made an algebra mistake. All right? How many of those do we end up catching a trout? 400. So in fact, we should probably have 3 things. How many do we have catching a bass? 250. And then we'll be left with 350 of nothing. So this would be event B. B equals catch something. And A would be catch a trout. And now if we do the expected counts approach, there's 650 times where we catch a fish. And of those 650, 400 are trout. Okay? If you actually cared about this problem, you could reduce. I don't really care about this problem. I can't pretend to care about this problem. I care about the method behind this. And the expected count is just a really good way to see what's going on. Okay? There's lots of ways of looking at this formula. So how many of you have taken a statistics class where you get to Bayes' formula? Okay. How many of you have heard, I think it's Simpson's paradox? Yeah, this is a good one. So we probably won't get to Simpson's paradox today. That'll probably come on Wednesday. But there's some incredible applications of this when we get up to Bayes' rule. Okay, so another way of looking at this is what's the probability of A given B? So we said it was the probability of A intersect B over the probability of B. There's another way of writing this. It's the probability of A intersect B divided by the probability of A intersect B plus the probability of A complement intersect B. So what's the probability of A intersect B plus the probability of A complement intersect B? What does that equal? Yes?
Probability of B.
It's just the probability of B. Okay? And the reason it's the probability of B is there's two ways B can happen. I don't think it's quite swinging far enough. Okay. There's two ways B can happen. B can happen with A or without A. And so what we're doing is we're breaking the event B up into two disjoint events, A intersect B and A complement. And if you look at it this way, I think this is a little bit more transparent as to what's going on, as to why this is the conditional probability. It's the fraction. Okay? It turns out all probabilities are conditional probabilities. Just take B to be omega. And so if you take B to be omega, it then just reduces to our old definition. And I have a small section in the book where I talk about multiplying by 1. The probability of omega is just 1. We're just dividing now by 1. But this is another way of looking at it. What's the probability of A happens given that omega happens? Well, omega always happens. Okay? We will be using this later on when we get to Bayes' theorem. What we're doing here is this is a partition. We're breaking a complicated event B into a bunch of simpler events. And we're trying to understand what's happening with those simple events. We've done this before. This is one of the big themes, is it's much easier to do a lot of simple problems than one very hard problem. Okay. So any questions on the definition of conditional probability? Of how we found this formula? Okay. So in practice, of course, just because we have this formula does not necessarily mean it's the best way to calculate an event. If you want to use this formula, you have to figure out what A is, what B is, and what A intersect B is. So here's a nice problem. I think I gave it with 2 jacks and a 4. I'll just make sure I use the same numbers. So I have 2 jacks and a 4. Okay. Given 2 jacks and a 4, what is the probability you draw 2 cards and end with 3 cards of the same number? So how could we end up with 3 cards of the same number? What's one way? So we could draw 2 4s. So we could have Jack, Jack, 4, and draw 2 more 4s. How else could we do it? Yes?
1 Jack and 1 not Jack.
Sure. We could have Jack, 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 4, and something else. In fact, that something else could be a Jack and could give us 4 Jacks. It could be a 4 and give us 2 4s and give us a full house. And then we have to be careful about double counting and making sure we go through all things. So maybe star means not Jack, not 4. So we could also have Jack, 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 4, and Jack, 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 Jack. I'm sorry, Jack, 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 4, 4. So those would be all the different ways that we could end up with at least 3 cards of the same number. Does this feel like a conditional probability? Yeah.
You know what cards you're looking for.
Yeah. That's the big clue, the word given that you have this. So what's the event B?
Sorry, can I just ask a question?
Yes.
So is it at least 3 or exactly 3?
At least.
Oh, okay.
Right? And this is where you have to be very careful in terms of how people phrase things. Years ago, did I tell you the ring story? I was visiting family in Maine, and we were walking, and we ran into one of their friends. It was after the Red Sox game, so we're chatting about how Wakefield did, and the conversation goes on, and the guy mentions the first time the Red Sox gave him a World Series championship ring. And Normal human beings do not say the first time unless there's a second time. Only pedantic people like mathematicians, maybe a few logicians, would say the first time when it's only happened once. So he has 3 World Series championship rings. Okay? Over here, you've got to be very careful. Is it at least or exactly? And the way I would interpret this is at least 3. If you're ever not sure, just shoot an email and just ask what is meant. All right, so here, the given is a huge clue. How many of you remember Calc 1? What's the key word to remind you to use the chain rule? If you hear a certain word, you should think chain rule when you're doing derivatives. So if I give you, cosine of 3x squared plus 5, you should be thinking chain rule. What's the key word that tells you it's a chain rule? Yes? Of. Whenever you hear of, you should be thinking chain rule. Cosine of, this is f of g of x. So certain words are just clues to tell you how to approach this. So this is similar to the of from calculus. So when you hear given, so event B is dealt jack, jack, 4. And then event A is at least 3 jacks or 3 4s. And now you would have to calculate the event A intersect B. And so sometimes for problems like this, it's better not to go through all the formal language and just say, look, I've already got 2 jacks and a 4. Here's my 4 cases. Let's just calculate what the probability of those 4 cases are and add. So what's the probability that we have 2 more 4s? Or maybe let's count the number of ways. How many ways can we get 2 more cards? So number of ways to get 2 more cards. What would that be? Yes? Good. Why is it 49 choose 2? We already have 3 in our hand. So since we already have 3 in our hand, there's only 49 cards available. So the number of successes, I have to draw 2 4s. How many ways are there to draw 2 4s? We already have 1 of them. 3 choose 2. There are 3 4s remaining. I have to choose 2 of them. Or I could draw a jack and something other than a jack or a 4. How many ways are there to do that? So first I have to choose a jack. 2 choose 1. I have 2 jacks remaining. I choose one of the 2 jacks. And now I have to choose a card that is neither a jack nor a 4. How many ways are there to do that? Why 48? Why 45?
Because we can't choose the 2 jacks or, oh wait, there's 3 4s. So it's 40. So it's 44.
It's 44. We can't have any jacks or any 4s. So there's only 44 cards left, and of those 44 cards, we have to choose 1. So it's 44, choose 1. Or we choose a jack and a 4. And so there is 2 choose 1 ways to choose a jack, and then 3 choose 1 way of choosing a 4. And then we would just divide. So sometimes it's better not to go through and formally write everything down. What is my A? What is my B? And to just do the calculation. Here, there's only 4 cases. It's not too bad to go through. If you think you may have made a mistake, you could try to do it another way. But what else could you do if you're worried that you made a mistake? Yes?
And the probability that you don't get any successes?
Right, but that would be similar to doing it another theoretical way. So if you think you might have made a mistake, you can try to do the problem another way theoretically. What else could you do?
And the probability of not hitting.
But that's still doing it theoretically. That's still trying to do another theoretical calculation. And let's just say you do not trust your theoretical calculations. Yes?
You could write a program that does this a bunch of times.
You could write a program that does this a million times, a billion times, right? And if your computer program runs this and gets a reasonable answer that matches what you got, then you can be very confident that you haven't made a mistake. It's not a coincidence that early in the semester we devoted one whole day to doing programming. Whenever you have something like this, write a short, simple code. This is not a hard problem to code, right? We only have jacks and fours. We talked in class on Friday about special cards, kings and queens. It's the same problem here. And you can write that code. And so as a really nice exercise, make sure you can write code for something like this. Let's revisit trump splits. So north and south have 8 trump. What is the probability someone in the east-west axis has all 5 remaining? So, is this a conditional probability? Yes. Why is this a conditional probability?
Given that 8 of them are in the north.
Right. I didn't write the word here, but I could have written the word given north-south have 8 trump. So we could set this up exactly as before with the A's and the B's. Now we had a really nice way that led to a simple calculation that sadly failed. Remember the field approach? What was the failed answer? Yes?
He was saying like each card had a 50% chance.
Yeah, each card had a 50-50 chance, so it was 1/2, which was 1 over 32. But then we had to multiply by 2 because there were 2 people, so we got 1 over 16. And the answer was, I think, 9 over 230. Was 9 over 230. Okay. So why did this method fail? Yes?
It was based off of the fact that there's now not there are repeats of cards in this number of them now.
So wait, why did this fail?
Because it doesn't take into account the condition that 8 of those trumps are in possession of.
No, because we have 5 remaining trump that we're trying to assign.
It's not choosing what a card or what hand, what person a card goes to isn't independent.
It's not independent. It's a conditional probability. Once I give you one card, does the next card have the same probability of going to you or going to the other person? So let's say I have to assign 13 cards to each of 2 people. Once I give you a couple of cards, the next card, there's more available spots for the other person than for you. So let's try to calculate the probability. Let's do it as a conditional calculation. What's the probability you get the first trump, the first of the 5? 1/2. I don't want to write it as 1/2. How should I write it? Maybe do I want to write it as 1/2? I don't want to write 1/2 as 1/2. No, I don't. Yes?
In bridge, are all the cards already dealt out?
They're already dealt out. But if you want, you can imagine you're dealing them. So I have 26 cards remaining that I have to assign, and 5 of them are trump. So I have 26 left, 5 are trump. So I agree that it's the probability that the first trump goes to one person is 1/2. But there's a better way of writing a half.
1 over 2 factorial.
Not 1 over 2 factorial, not a bad guess. Yes?
1 over 2 choose 1.
Not 1 over 2 choose 1. So why is it 1/2? I've got 13 spots for one person, 13 spots for another. Not 2 choose 1. It's 13 over 26. There are 13 spots for the first person that are free. There are 26 spots total. And that should be the probability that the first trump goes to the first person. Now that they have a trump, what's the probability that they get the next trump? What do you think it should be for the next one? Was your hand up, or? 12 over 25. And what do you think the next one should be? 11 over 24, 10 over 23, and then 9 over 22. Some of these are very easy to do the algebraic simplification. 13 over 26 is 1/2. Okay? And then when we do all the algebra, we get 1/2 times 9 over 230. So we almost had the same answer as before. What do we have to remember to do? Two people. So we should put in a 2 choose 1 because there's 2 people. And then when we do that, now we get 9 over 230. And this will give the same answer. This is another way to get the answer for how many ways are there to get a 5-0 split. What is the probability? And what, yes?
Why do we not take into account the other cards in the deck?
Doesn't matter. If you want, I've just got 5 cards that I need to assign. I don't really care who gets the remaining. I just care, is this card in your hand or not? And if you think about what's going on, every time you have a card, each card is equally likely to go into any spot. And if you want, I can always reorder my hand so that the trumps are the first cards. It's not going to affect anything. So there's a lot of equivalencies you can do that really won't change what's happening. So I want to show lots of different ways of doing these problems because some ways click more for some people rather than others. There's lots of different ways of looking at these calculations. The first is to notice, is it a conditional probability? And then what is the easiest way to do that conditional calculation? Okay? Now, what should be clear from this is that it is much easier not to have to worry about conditional probabilities. It's much nicer when events A and B are independent. So there's a lot of formal definitions of independence. Informally, we say 2 events are independent if the probability of one does not affect the probability of the other. Okay? Can someone give me 2 events that are probably independent? Flipping a coin twice. So you've got to be careful. Maybe when you flip the coin, you always flip the coin the same way. And how the coin lands, maybe you then use that to initialize how you flip the second time. So it's very easy to have dependencies. For the record, I have 3 jobs on my son's soccer team. One is I'm in charge of the coin flips, and we have yet to lose when I have been in charge of the coin flips. Someone else flips the coin, but I help us choose which side we want. So it's got to be very careful. I want 2 events that are clearly independent. Yes?
Flipping a coin, hitting a heads, and rolling dice.
Okay, these are 2 completely different events. They shouldn't matter. Right? The outcome of tossing the coin should not affect how the die rolls. Okay? So what we want to do is, as much as possible, we want to study independent events. Independent events are much, much easier to look at. And so for conditional probability, we have the probability of A given B is the probability of A intersect B divided by the probability of B. Now, I haven't specified anything before about B, but in your mind, you should be thinking something about the event B. What should you be thinking? Yes?
B has to have a non-zero.
Yes. And the probability of B, as was just mentioned, should be greater than 0. What's the probability of A happens given that B doesn't given that B happens. Oh, and by the way, B never happens. You should not be able to make statements like that. Okay? And if you try to put this in, if the probability of B is 0, what's the probability of A intersect B? 0. So you get 0 over 0. Great, it's undefined. So it's telling you, don't even try to assign a probability to this. Okay? We should only be using this. Oh, and actually I could do payback to a grad student. Wonderful. Now, when you see an equation like this, what might you like to do? So how could I rewrite this equation?
Split up the probability of B,
Not split up the probability of B.
Just move the probability of B to the other side.
Yeah, move the probability of B to the other side. And just write this as the probability of A and B is the probability of A given B times the probability of B. Now this makes sense even if the probability of B is 0. When I was an undergraduate, I could not take stats from the stats department. It didn't fit into my schedule, so my lab partner and I were forced to take it from the psych department. And we were physics majors, math majors. On one of the midterm questions, we needed to use the concept of the mean. And rather than writing the mean as the sum of xi divided by n, my lab partner wrote n times the sum of xi is the mean and was marked wrong by the psych grad student. We then brought Rudin's principles of mathematical analysis to show you can multiply both sides. And the psych grad student said, if you stop bothering me, I'll give you half credit. And so we said, if you're willing to write that this is only worth half credit, we'll stop bothering you. So my lab partner, I believe, still has to this day a exam where he gets only half credit because he multiplied through an equality. We were not in danger of not getting A's for the course. We were quite happy to take the 5 points off. You may multiply. Okay? And in fact, sometimes when you multiply, it makes things more illuminating. The probability of A given B times the probability of B. And this leads to a really good notion. So we would say events A and B are independent when the probability of one has no influence on the probability of another. So if A and B are independent, what should the probability of A given B be? Well, yeah, so if independent should be the probability of A. And this becomes a really nice condition for independence. A and B are independent if the probability of A and B is the probability of A, the probability of B. And when you have independent events, then it means these compound events, when they both happen, is just a product of the probabilities. Okay? Are there only 2 events in the world? No. So then the question becomes, what if you have 3 events? What should the notion of the probability of 3 events being independent be? So now you want, I want to ramble for a little bit longer. So you want to have A, B, and C. So what does it mean for A, B, and C to be independent? Yes?
Probability A intersect B intersect C is equal.
Okay, so the most natural thing to try, as was just said, is the probability of A intersect B intersect C is the probability of A times the probability of B times the probability of C. Right? So now let's say we roll a fair die. A will be first roll is even. B is first roll is odd. And C will be sum is even. What's the probability of A?
Can we say that it's independent if the sum is even, though, because that relies on what we got?
Which is the sum of the 2 rolls is even. So here's a problem to consider. Are these three events independent? What's the probability that A happens? A half. What's the probability B happens? A half. What's the probability C happens? Half. It doesn't matter what the first row is. If the first row is an even number, then the sum is even if your second row is even. If the first number is odd, so C also has probability 1/2. All of these events have probability 1/2. Now, what about the probability that A intersect B intersect C happens? That the first row is even, the second, I'm sorry. I had meant to write the second row is odd, but we'll do it this way. So what's the probability that A and B and C happen? That would be 0, right? So these events are clearly not independent, which makes sense. If I know that A and B happen, okay, A and B can't happen together. So that's not event. Let's do now that the second row is odd. What about now? Are these events independent? No. Again, if A and B both happen, then C can't happen. So here's a situation where the product of the probabilities is not the probability of the intersection. They're not going to be independent. It turns out that there is a way to choose three events such that the product of A intersects B intersects C is the same as the product of the probabilities. This is not enough for independence. So I'll leave you to read that, or even better, to try to play and come up with your own example. This is insufficient. So it's not a sufficient condition. It's not enough that the product of A intersects B intersects C is the probability of A intersects times probability of B times probability of C. So there's an example in the book, but better than that, try to find your own example. What do you think is going wrong here? Yes?
If the probability of A, B, or C is 0, it just kind of falls apart.
So one thing is it falls apart if one of the events can't happen. And so one question is, can you come up with an example where A, B, and C all have positive probabilities? So the first thing is you've absolutely demolished this, which is great. But then I'll say, okay, well, I meant to add this condition that all the probabilities are positive. There's still a counterexample where all the probabilities are positive. So if we want A, B, and C to be independent, what else do we want to be independent? Yes?
The
Pairwise. Also want pairwise independence. So we also want the probability of A intersects B equals the probability of A, probability of B. We also want the probability of A intersects C to be the probability of A, probability of C, and the probability of B intersects C to be the probability of B, probability of C. It makes sense. If we want to extend up to the point where we have A, B, and C are independent events, well, then A and B should also be independent, B and C should be independent, and A and C should be independent. And so we need to include these. So as we go higher and higher and higher, if we look at the more general case, if we want a bunch of events to be independent, then all the intersections should factor, and not just the big one at the end. And then that will be enough to assert true independence. Okay, any questions on this? So this is a good definition of independence. Basically it says the probability of the intersection is the product of the probabilities. Okay, so now this gives us the general multiplication rule. Let me see how much time we have left. We have about 5 minutes left. Okay, so we can either do the Monty Hall problem or we can do the 3 hats problem. First loud voice wins.
3 hats.
3 hats. Sorry. Here. All right. So this is, I think, my favorite conditional probability problem. And the reason I like it is it is not just cookbook mathematics meant to just teach you a concept. It's actually something that's used in the real world. So 3 hats. There's lots of versions of problems like this. This is a great colloquium topic. You have 3 people, and you're going to randomly put a hat on each person. And the hats are either white or black, each independently done. Each happens half the time. Okay, so each person gets a white or black hat independent of the other 2 people. All right, and the 3 people are in some kind of triad formation. Maybe that person has the white hat, black hat, black hat. Each person can see the other 2, but not see themselves. And you go, close your eyes, 1, 2, 3, open. You have 5 seconds to stare, and then you either say white, black, or stay silent. Do you want the money version or the brutal version? Okay, so if even one person speaks and is wrong, the 3 people are brutally killed. They are forced to watch Punky Brewster marathon until they just die of boredom. They die in a very painful way. All right, so if even one person speaks and is wrong, everyone dies. But if everybody who speaks is correct, not only do you live, but you get $1 million. Okay? Can someone give me a strategy that will ensure that at least half the time, just 1 second, the team survives? So again, you don't have to speak, but everybody has to speak at the same time.
Well, there's always going to be 2 of...
Well, no, I want a strategy, a simple strategy, so that half the time...
You only speak if you see 2.
I want, no, you're giving me the correct, I don't want the full answer. I want an answer such that half the time you will be right and half the time you'll be wrong.
Pick one person to randomly.
One person randomly guesses. And if one person randomly guesses, since the hats are randomly placed, you have a 50-50 chance. Okay? So here's a strategy so that you have a 50-50 chance of living. All right, now I'll turn to you and say, can you give me a strategy where you do better than 50%? You speak up if you see 2 of one color, and then you see the opposite. So if you look at all the cases, it's white, 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 black, white, 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 black, white. Then I want to do white, white, black. Now I have to do 2 blacks. Black, black, white, black, white, black, white, black, 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 white. Or did I do that? No, I did that one. So it's all black, black, black. There are 8 possibilities. Of these 8 possibilities, if you speak when you see the other 2 that are the same color, you lose here. In fact, all 3 of you speak wrong, and all 3 of you speak wrong here. In these cases, only one person speaks. First person speaks and is right. Second person speaks and is right. Third person speaks is right. Third person speaks is right. Second speaks is right. First is right. Notice everybody speaks 4 times. Everybody is right twice. Everybody is wrong twice. And everybody is silent 4 times. You should not be able to be right more than half the time if your hat is randomly chosen. What we've done is when you are wrong, boy, is your team wrong. We concentrate the errors. And we spread out the right. And so by doing this, you have 6 out of 8 cases where you get the right answer. This is used in error detecting and error correcting codes, where when you're transmitting information, computers use algorithms like this to determine if a digit has been mistransmitted or misreceived, and fixes it in real time, so you don't have to download the whole file again. So this is one of the best applications I know of conditional probabilities. What is the probability you have a white hat? Well, depending on what you see, that actually can be used. And as a nice exercise, try to figure out, well, what if we had more than 3 people? What's the next natural number to look at? So 3 is a special number for many ways. You have to try to decide in what way is 3 special, what's the next special